something is wrong with the universe. Not in a metaphorical sense, not in the way philosophers sometimes describe the existence or the cruelty of entropy. In a literal, measurable, data-confirmed sense, something is wrong with the universe. And the machine that found it is the most powerful eye humanity has ever pointed at the sky. The James Webb Space Telescope cost $10 billion. It took 30 years to design, build, and launch. It carries a mirror nearly 7 meters across, folded like origami to fit inside its rocket, then slowly, over the course of 2 weeks in the vacuum of space, unfolding itself into a structure of almost incomprehensible precision. It is stationed 1.5 million kilometers from Earth, orbiting a gravitational equilibrium point where the pulls of the Earth and the Sun cancel each other out, a stable platform from which to look deeper into the universe than anything before it. Its first images were released to the world on July 12, 2022, and they were extraordinary. Fields of galaxies so dense and so distant that each point of light represented not a star, but an entire galaxy. Hundreds of billions of stars compressed by distance into a single pixel. The light in those images had been traveling for over 13 billion years. Webb was seeing the universe not as it is now, but as it was when the Earth was not yet born, when our solar system did not exist, when the atoms that make up your body were still dispersed across the void of space. Infant galaxies, the first light after the cosmic dark ages, the dawn of everything. The world was captivated. Scientists wept. Politicians made speeches. The images were shared billions of times, and most people watching those images, most people staring at that deep field photograph and feeling the vertigo of cosmic scale, thought this was the story. That the extraordinary beauty of what Webb could see was the point, that the story was about wonder, about human achievement, about the triumph of science. They were wrong, because what Webb found in those first images, and in the months and years of data that followed, was not what cosmologists expected, not what the models predicted, not what any simulation of the early universe had ever produced. The galaxies Webb found in the deep universe were too big, too mature, too structured, and too numerous to have formed in the time available. They were, in the technical language of astrophysics, impossibly early galaxies. And the more data Webb gathered, the worse the problem became. But the impossible galaxies were only the beginning. Webb also found something in the spectra of an exoplanet's atmosphere that has sparked one of the most cautious and most intense debates in astrobiology, a chemical signal that, on Earth, is produced almost exclusively by living organisms. It found anomalies in the large-scale structure of the universe that deepen a crisis in cosmology already underway. It confirmed that the universe's rate of expansion does not match the predictions of the standard model, at a level of statistical certainty that rules out measurement error. It found objects that should not exist at the distances they occupy. It found chemistry that should not be present in the atmospheres it sampled. And every time the data came in, astronomers checked their instruments, rechecked their calibrations, questioned their assumptions, consulted their colleagues, ran the numbers again, and arrived at the same conclusion. The universe is not behaving the way we thought it would. Something is wrong. And the James Webb Space Telescope is the instrument that has made that wrongness impossible to ignore. In the next 90 minutes, we're going to examine each of these anomalies in detail. We're going to look at the science, of the scientists, of the theories, and at what it would mean for reality itself if those theories turn out to be true. Prepare yourself, because what Webb has found is not just scientifically surprising. Some of it is deeply, genuinely terrifying. To understand why what Webb found is so disturbing, you first need to understand what it was built to find, and why the difference between expectation and reality matters so enormously. The James Webb Space Telescope was designed as the successor to Hubble, the workhorse of astronomical observation since 1990. Hubble operates primarily in visible light and ultraviolet radiation. It can see far into the universe, but not to its very earliest epochs. The most distant objects in the observable universe are so far away that the expansion of space has stretched their light into the infrared. By the time light from the first galaxies reaches Earth, it has been redshifted far beyond what Hubble's detectors can see. To observe the cosmic dawn, you need an infrared telescope, and here lies the engineering challenge that made Webb so extraordinarily difficult and so extraordinarily expensive to build. Infrared radiation is heat radiation. Every warm object emits it. a telescope sensitive enough to detect the faint infrared glow of a galaxy 13 billion light-years away must be cooled to temperatures close to absolute zero, because any warmth in the instrument itself would drown the signal and noise. Webb solved this problem with a sunshield the size of a tennis court, a 5-layered membrane of aluminized kapton, each layer thinner than a human hair, that blocks the heat of the sun and allows the telescope's mirror and detectors to cool to minus 233 degrees Celsius, just 40 degrees above absolute zero. Cold enough that the thermal noise in the detectors is reduced to essentially nothing. Cold enough the Webb can detect a single photon of infrared light from the edge of the observable universe. What cosmologists expected Webb to find in the deep universe was entirely consistent with the standard model of cosmology, the lambda CDM model that has successfully described the large-scale structure of the universe for decades. They expected small, irregular, primitive galaxies, the seeds of cosmic structure, the earliest clumps of matter that would eventually, over billions of years of mergers and accretion, grow into the grand spirals and ellipticals we observe in the nearby universe. These early galaxies should have been dim blue and sparse blue, because the most massive, shortest-lived stars form earliest, and sparse because the early universe had not yet had time to assemble much stellar mass. That is not what Webb found. In December 2022, a team led by Ivo Labbé at Swinburne University of Technology published a paper in the journal Nature that caused an immediate and significant stir in the astrophysics community. Using data from Webb's first deep-field observations, Labbé's team identified 6 massive red, compact galaxies, objects they privately called the Red Monsters, at redshifts placing them in the first 500 to 700 million years of cosmic history. The universe at the time those galaxies existed was barely 5% of its current age. The mass of these galaxies was what shocked astronomers. To match their observed brightness and color, the galaxies had to contain stellar masses of between 10 billion and 100 billion times the mass of our Sun. One of the 6 was, by stellar mass, comparable to our entire Milky Way galaxy, assembled when the universe was barely 500 million years old. This was, by every standard model of galaxy formation, impossible. Joel Leisure of Penn State University, one of the paper's co-authors, put it in terms that have been quoted widely ever since. Finding these objects, he said, was like finding a 45-year-old man in a kindergarten class. They should not be there. The standard model had been built and tested and refined over decades of observation. It worked. It predicted things, and the predictions came true. And now Webb was showing it something it could not predict and could not, in its current form, explain. But that was only the beginning. As Webb continued to gather data through 2022 and 2023, the picture did not improve. It got worse. Significantly worse. Additional surveys of the early universe found more of these massive early galaxies. Not 6, not 60. Hundreds of candidates, all at redshifts placing them in the first billion years of cosmic history, all more massive and more structured than the standard model allows. Researchers began calling the situation the impossible early galaxy problem, a phrase that captures the essential tension. These objects exist in the data, and the data is good, and the standard model says they cannot exist. In 2023, Natalie Allen and colleagues at McGill University published an analysis finding that the density of massive galaxies in Webb's deep fields was approximately 50 times higher than expected, not 50% higher. 50 times, 2 full orders of magnitude. This is not the kind of discrepancy that gets resolved by a recalibration or a revised parameter estimate. This is a discrepancy that challenges fundamental assumptions about how the universe works. And then, Webb did something the field was not prepared for. It found old red galaxies that had already stopped forming stars, what astronomers call quenched galaxies. At very high redshifts, galaxy formation under the standard model is a long and gradual process. Quenching, the shutting off of star formation across an entire galaxy, requires a specific set of conditions that take time to develop. A sufficiently massive central black hole whose jets heat the gas and prevent it from cooling, or the exhaustion of the galaxy's gas supply, or some large-scale feedback mechanism. Quenching should not happen in the first billion years of the universe. Webb found quenched galaxies at redshifts, suggesting they existed 600 million years after the Big Bang. Galaxies that had already lived full lives, formed all their stars, processed all their gas and gone dark, at a cosmic age when, by the standard model, the universe should barely have been capable of forming any stars at all. Italian astronomer Francesco Valentino, analyzing one of these objects, described it in his 2020 paper as a galaxy that should not be dead because it should not yet have fully been born. Michael Boylan-Colchin at the University of Texas Austin published a detailed statistical analysis of the problem in Nature Astronomy in 2023. His paper, Stress Testing CDM with High Redshift Galaxy Candidates, used the most extreme of Webb's early galaxy discoveries to quantify just how badly the standard model was failing. His conclusion was stark. The number of massive galaxies detected by Webb at the highest redshifts was inconsistent with the standard model at a level of statistical significance that could not be dismissed as noise. These galaxies should simply not exist given our current understanding of the universe, Boylan-Colchin told reporters in interviews following the paper's publication. Webb has revealed a tension that demands either new physics or a serious revision of how we model galaxy formation. And all of this was happening while, simultaneously, Webb was doing something else entirely, something that had nothing to do with the early universe and everything to do with one of the most profound questions humanity has ever asked. What they discovered next shocked the scientific community. Before we go further, we need to understand something important: how Webb actually gathers its data, and why its observations are trusted by the scientific community, even when those observations appear to contradict everything we thought we knew. The James Webb Space Telescope gathers light using 4 primary scientific instruments. NIRCam, the near-infrared camera, is Webb's primary imaging instrument, capturing light at wavelengths between 0.6 and 5 microns, extending from red visible light well into the infrared. Its sensitivity and resolution in this range surpass anything that has come before it. NISPEC. The near-infrared spectrograph breaks the light from up to 100 objects simultaneously into its component wavelengths, producing the spectra that reveal chemical composition, temperature, density, and velocity of distant sources. MIRI, the mid-infrared instrument, extends Webb's reach into longer infrared wavelengths, detecting dust-shrouded objects invisible to NIRCam and providing crucial data about the cool, dusty environments of distant galaxy formation. And FGS/NIRIS, the fine guidance sensor, a near-infrared imager and slitless spectrograph, handles precision pointing and provides additional spectroscopic capability. The key to understanding what Webb found and why it matters is the concept of the spectrum. Every element and molecule, when it absorbs or emits light, does so at specific characteristic wavelengths, a fingerprint unique to that substance, determined by the quantum mechanical energy levels of its electrons. By spreading the light from a distant object into its component wavelengths and measuring the intensity at each wavelength, astronomers can determine the exact chemical composition of whatever the light passed through. This is how Webb identifies carbon dioxide in the atmosphere of an exoplanet 100 light-years away. This is how it determines the chemical composition of galaxies at the edge of the observable universe. This is how it measures the recession velocities of distant galaxies, by the shift in their spectral lines, the Doppler-like redshift caused by the expansion of space. The spectra Webb produces are extraordinarily precise. The telescope's primary mirror, 6.5 meters across, made from 18 hexagonal segments of gold-coated beryllium, aligned to within nanometer tolerances using actuators that can make adjustments smaller than the diameter of a single atom, collects light with an efficiency and resolution that fundamentally exceeds Hubble's capability in the infrared by factors ranging from 10 to more than 100, depending on wavelength. This precision is why Webb's findings are so deeply unsettling. These are not the results of a poorly calibrated instrument. They are not artifacts of a flawed detector or a misaligned mirror. They have been verified by multiple independent teams using multiple analysis methods, cross-checked against data from other telescopes wherever possible, and submitted to peer review, the adversarial self-correcting mechanism of science, before publication. When Webb's findings disagree with the standard model, the disagreement is real. The universe, when measured by the most precise instruments humanity has ever built, does not match our models. And if you understand how those models were built, how carefully, over how many decades, by how many brilliant people, tested against how many independent observations, then you begin to understand why that sentence is not a minor academic footnote. It is a crisis, a genuine, unresolved, productive, terrifying scientific crisis. The standard model of cosmology, lambda CDM, describes the universe as composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. It correctly predicts the temperature and polarization patterns of the cosmic microwave background, the large-scale distribution of galaxies, the abundance of light elements formed in the first minutes after the Big Bang, and dozens of other observational tests. It is one of the most successful predictive theories in the history of science, and Webb is finding things it cannot explain. If you're fascinated by where science breaks down and rebuilds itself, subscribe. We have much more to explore. The impossible early galaxies are the most dramatic and most visible of Webb's anomalies. But they are not the only one. There is a deeper problem, older, more carefully documented, more mathematically precise, that Webb has now made significantly worse. It is called the Hubble tension, and it may be the most important unsolved problem in all of modern physics. The Hubble constant, written as a keypin and named for Edwin Hubble, who first measured the expansion of the universe in 1929, is the number that describes how fast the universe is expanding. Its units are kilometers per second per megaparsec. For every additional megaparsec of distance between 2 points in the universe, those points are moving apart here's a additional kilometers per second. It is one of the most fundamental numbers in cosmology, a number that, combined with other cosmological parameters, defines the age of the universe, its future fate, and the geometry of space itself. The problem is that there are two completely independent methods of measuring it, and they give different answers. The first method begins at the beginning of the universe itself, the cosmic microwave background. The oldest light in the universe emitted approximately 380,000 years after the Big Bang, when the universe first became transparent, contains, encoded in its temperature fluctuations, a precise record of the cosmological parameters that govern the early universe. The Planck satellite, which mapped the CMB with extraordinary precision between 2009 and 2013, extracted those parameters and used the standard model of cosmology to predict the current expansion rate. The Planck measurement gives measurements, a sensori of approximately 67.4 kilometers per second per megaparsec. The second method measures the expansion rate directly in the nearby universe using what astronomers call the cosmic distance ladder. It begins with the parallax of nearby stars, the tiny shift in their apparent position as Earth moves around the Sun, which gives their distance with geometric precision. It then uses Cepheid variable stars, stars that pulsate with periods directly related to their luminosity, to extend the measurement to nearby galaxies. And it uses the peak brightness of type Wiener supernovae, explosions so bright they can be seen across billions of light-years, to extend the measurement to the distant universe. The distance ladder measurement gives HK of approximately 73.0 kilometers per second per megaparsec, 67.4 versus 73.0. The numbers sound close. They are separated by only about 8%. But in the language of statistical significance, the discrepancy is at the level of 5 sigma, a 1 in 3.5 million probability that it is due to random measurement error. 5 sigma is the threshold physicists use to declare a discovery. At 5 sigma, statistical noise is essentially eliminated as an explanation. Something real is causing these two measurements to disagree. Before Webb, some researchers argued that the high-distance ladder value of Bochum-Bohr-Aha was an artifact of systematic errors in the Cepheid measurements. Cepheids are variable stars, and measuring their periods and luminosities accurately requires carefully controlled observations that could, in principle, be affected by the crowded environments of nearby galaxies. A better telescope, with high resolution and infrared sensitivity, might reveal these systematic errors and bring the two values into agreement. In February 2023, a team led by Adam Rice, who shared the Nobel Prize in Physics in 2011 for discovering the accelerating expansion of the universe, published the first Webb measurements of Cepheid variable stars used in the distance ladder calibration. Rice's team used Webb's NIRCam to observe Cepheids in galaxies where they had previously been measured by Hubble, checking for systematic errors introduced by the crowded environments of those galaxies. Webb found no significant systematic errors. The Cepheid measurements made with Hubble were confirmed. The high value of HEK from the distance ladder was confirmed. The Hubble tension survived its most important test, not weakened but strengthened. Rees wrote in the paper that the tension had survived its most stringent test to date and was now harder to attribute to systematic errors. In the precise, hedged language of scientific papers, this is a statement of alarm, translated into plain language. The crisis is real. The discrepancy is not a measurement artifact, and the standard model has a problem we do not know how to fix. And then things became even stranger. In September 2023, a paper appeared in the astrophysical journal Letters that sent shockwaves through the astrobiology community and into the popular press. It was published by a team led by Niku Madhusudan at the University of Cambridge, and it reported something that had never been reported before in the peer-reviewed literature. Webb had detected in the atmosphere of an exoplanet called K218b tentative evidence for the presence of a molecule called dimethyl sulfide. Dimethyl sulfide, DMS, is a molecule of modest complexity, two methyl groups attached to a sulfur atom. On Earth, it is produced in significant quantities, almost exclusively by marine phytoplankton and other biological organisms. Certain sulfate-reducing bacteria produce small amounts of DMS in anaerobic environments. No significant geological, volcanic, or purely chemical process is known to generate DMS at the concentrations found in Earth's oceans and atmosphere. If DMS were present in the atmosphere of K218b at detectable concentrations, the most plausible source, by far, would be biological. K218b orbits a red dwarf star 120 light-years from Earth. It is approximately 8.6 times the mass of Earth and 2.6 times its radius. This places it in a class of worlds intermediate between Earth and Neptune, worlds that planetary scientists call sub-Neptunes. Madhusudan's own research group had proposed that a subset of these worlds might be Haitian planets, worlds with global oceans of liquid water beneath thick hydrogen-rich atmospheres, potentially hosting conditions similar to Earth's deep ocean, where marine organisms thrive in the absence of sunlight. K218b sits in the habitable zone of its star, at a distance where liquid water on its surface is, in principle, possible. Webb observed K218b during A-transit's passages of the planet across the face of its star, accumulating enough photons to build up a precise spectrum of the light that had passed through the planet's atmosphere during each transit. The spectrum showed strong features of carbon dioxide and methane. It showed a signal consistent with water vapor, and it showed at the specific wavelength absorbed by dimethyl sulfide, a feature that could not be easily attributed to any other known molecule in the expected atmospheric composition. Madhusudan's team was extraordinarily careful in how they reported the finding. The DMS signal was at approximately 2 to 3 sigma statistical significance, suggestive, but below the 5 sigma threshold for a discovery. They explicitly acknowledged that the signal might not be real, that further observations were required, and that even if the DMS feature were real, non-biological explanations could not yet be definitively ruled out, though they noted that no convincing non-biological mechanism for producing DMS at detectable levels in K218b's type of atmosphere was known. The debate that followed was immediate and intense. David Charbonneau at Harvard, one of the world's leading exoplanet observationalists, urged extreme caution. The spectrum, he argued, was being pushed to its limits of interpretation, and the DMS detection was at a level where systematic uncertainties in the data reduction pipeline might generate spurious features. Bjorn Benneker at the University of Montreal, who had been studying K218b for years, was similarly measured in his response. Sarah Sager at MIT, whose career has been devoted to developing the theoretical framework for detecting biosignatures in exoplanet atmospheres, took a different tone. The finding was exactly what Webb was designed to produce, she argued, and the appropriate scientific response was not to dismiss it, but to schedule more observations. The fact that the signal was tentative was not a reason to ignore it. It was a reason to look again. Those follow-up observations are ongoing. The Madhusudan team applied for and received additional Webb time to observe K218b across more transits, accumulating more signal. As of the writing of the script, the result of those additional observations has not been published. A signal from a possible living ocean 120 light-years away, detected in the infrared by a space telescope that cost 30 years and $10 billion to build. Unconfirmed, unexplained, and impossible to stop thinking about. The anomalies revealed by Webb have not gone unnoticed by the scientific community. They have sparked an intense, ongoing debate carried out in papers, at conferences, in the preprint servers that have become the real-time bulletin board of modern physics, and in the public press. Understanding the scientists at the center of this debate helps clarify both the nature of the problem and the range of possible responses. Ivo Labe, the Australian-Dutch astronomer whose team first identified the 6 red monster galaxies in December 2022, has been both scientist and reluctant spokesman for the crisis. He is careful in interviews and in print to distinguish between what the data shows, massive red, early galaxies whose stellar masses exceed anything the standard model predicts, and what the data means, which remains genuinely uncertain. His paper in Nature was scrupulously worded, its conclusions carefully hedged, but the phrase he used to describe his reaction to the first results, "It's bananas," has become, in the astronomical community, something of a shorthand for the state of the field. Joel Layer of Penn State University has gone further in public statements, arguing that the Webb findings cannot be dismissed as calibration artifacts or analysis errors. "We've used these same techniques on tens of thousands of galaxies," he has said. "The methods are solid. The galaxies are real. The masses are real. The problem is real." Laja has invested significant effort in exploring whether active galactic nuclei, the accreting supermassive black holes at the centers of some galaxies, which can outshine the galaxy's stars, might be inflating the apparent brightness of Webb's early galaxies and leading to overestimates of their stellar mass. He has found that AGN contamination can explain some, but not all, of the excess. Erica Nelson of the University of Colorado Boulder, who led a separate analysis of early Webb data that confirmed the existence of massive early galaxies, has described the situation with a characteristic mixture of excitement and alarm. Her reaction when the first results came in, "My jaw dropped," was not the typical language of an academic scientist presenting findings at a conference. It was the language of someone who had spent years building models of galaxy formation and was now watching the observations smash those models. Adam Rice, whose 2023 Webb-based confirmation of the high Hubble constant cemented the reality of the Hubble tension, has spoken publicly about what the tension implies. He believes it points toward new physics, something in the universe that the standard model does not contain. He is, by temperament and by scientific habit, an optimist. He sees the tension as a discovery waiting to happen, rather than a crisis without resolution. But he is clear that the discovery, when it comes, will require something genuinely new. "We're not going to fix this with a small correction," he told the journal Science in 2023. "Something fundamental is missing." Niku Madhusudan at Cambridge has, in the aftermath of the K218b paper, been careful to neither oversell nor undersell what was found. He is a theoretical astrophysicist who understands both the power and the limits of spectroscopic detection, and he knows that the community's skepticism about the DMS detection is scientifically appropriate. "Science requires extraordinary evidence for extraordinary claims," he has said. "We are not claiming extraordinary evidence. We are claiming an interesting signal that merits follow-up." It is, in its way, a model of scientific communication in an era when the line between reporting and sensationalism is easily blurred. And then there is Prayambada Natarajan of Yale, one of the world's leading theoretical astrophysicists and a deep thinker about the implications of Webb's findings for the standard model. Natarajan has argued, in papers and in public, that the impossible early galaxy problem is a genuine theoretical crisis, that it cannot be explained by existing galaxy formation models, even when those models are pushed to their limits, and that something new is required. Her own proposals involve modifications to how the very first generations of stars and black holes formed and evolved, with seeded massive black holes possibly providing the gravitational scaffolding for rapid galaxy assembly. The proposals are speculative, but they are grounded in physics, and they represent the kind of creative theoretical response that major observational anomalies historically demand. The debate continues. The data is real. The anomalies are real. And the scientific community is doing what it does best, refusing to accept an easy answer. The impossible early galaxies and the Hubble tension are not the only anomalies Webb has revealed. There is a third, quieter in the press, but in some ways the most structurally significant, that concerns not individual galaxies but the large-scale organization of matter in the early universe. The Standard Model of Cosmology predicts that the very early universe was extraordinarily smooth. The cosmic microwave background, the oldest observable light, shows temperature fluctuations of only about 1 part in 100,000. These tiny temperature fluctuations corresponded to tiny density fluctuations, regions of space slightly denser than average, and regions slightly less dense. Over the next several billion years, gravity did its patient, relentless work. The dense regions attracted more matter, grew denser still. The less dense regions lost matter to their neighbors and grew emptier. The result, over 13.8 billion years, is the cosmic web we observe today. The vast three-dimensional network of galaxy filaments, clusters, and supervoids that fills the observable universe. But this amplification of structure takes time. The very early universe, in the first few 100 million years, should still be only minimally structured. Individual galaxies are beginning to form, but clusters of galaxies, superclusters, the large-scale filamentary web. These are features that require billions of years of gravitational evolution to develop. The early universe, in the Standard Model, is a place of seeds, not forests. Webb is finding forests. In 2023, multiple teams analyzing Webb's deep field images identified what appear to be proto-superclusters, early assemblies of multiple massive galaxies, at redshifts placing them in the first billion years of cosmic history. These are not random clusters of 2 or 3 galaxies that happen to appear close together on the sky. They are coherent multi-galaxy structures showing signs of gravitational organization, the kind of clustering that, in the Standard Model, requires several additional billions of years to develop. One structure identified by a team at the University of California, Santa Cruz, unofficially called El Gordo's ancestor by its discoverers, appears to be a proto-supercluster at a redshift, corresponding to a cosmic age of 900 million years. It should not, by any Standard Model prediction, be there in the form it appears. A separate statistical analysis of the distribution of galaxies in Webb's deep fields has found hints of a periodicity in their spatial arrangement, a regular pattern of spacing between galaxy concentrations, reminiscent of the baryonic acoustic oscillations that are a well-established feature of the universe's large-scale structure at lower redshifts. Baryonic acoustic oscillations are the frozen imprint of sound waves in the early universe, waves that travel through the hot plasma of the first 380,000 years and left a characteristic scale imprinted on the distribution of matter when the universe first became transparent. Finding BAO-like signatures at very high redshifts would imply that the matter distribution was already organized, at those early times, in ways that should not yet have developed. These findings are preliminary, and the astronomical community is appropriately cautious about interpreting high redshift structure from data that is still being analyzed and calibrated. But the direction of every anomaly is consistent. The early universe, as seen by Webb, is more structured, more evolved, and more complex than the Standard Model predicts. This is not a coincidence of statistical noise pointing in the same direction. It is a pattern, and in science, when a pattern appears in multiple independent datasets pointing consistently in the same direction, you take it seriously. Even when, especially when, it is pointing towards something you did not expect and do not yet understand. The early universe was supposed to be simple. It is not, and that simplicity, or its absence, changes everything about what we thought we knew. Let us step back from the individual findings and ask the larger question that all of this data demands. What would it actually mean if the Standard Model of cosmology is wrong? The answer depends on how wrong. And there is a spectrum of possibilities, ranging from the relatively modest, a refinement or extension of the existing framework, to the deeply transformative, involving a fundamental revision of our understanding of the universe's composition and history. At the modest end, the Standard Model might need to be extended in specific ways that preserve its basic architecture while adjusting some components. The impossible early galaxies, for example, might be explained by modifications to the physics of the very first stars and galaxies, modifications that made the process of galaxy assembly more efficient in the early universe without requiring changes to the fundamental parameters of dark matter, dark energy, or the Big Bang itself. If early stars formed more massive than current models predict, they would have produced more energy and more heavy elements per unit of stellar mass, potentially seeding more rapid galaxy growth. If the very first generation of black holes was more massive than expected, seeded, not by the collapse of individual stars, but by the direct collapse of large gas clouds. Those seed black holes could have provided the gravitational scaffolding for rapid galaxy assembly. Several such modifications have been proposed. None of them fully explains all of Webb's observations, but they represent the kind of targeted, physically motivated adjustment that has historically been how good models are improved. At a more significant level, the Hubble tension, the 5 sigma disagreement between the early universe and late universe measurements of the expansion rate, might require what physicists call new physics, genuinely new components or behaviors of the universe not included in the standard model. The most discussed proposal is early dark energy, the idea that the cosmological constant, instead of being truly constant, had a higher value in the early universe than it has today. Early dark energy models can, in some versions, bring the 2 Hubble constant measurements into better agreement. But they tend to create new disagreements with the detailed CMB data. The search for a modification that resolves the Hubble tension without breaking other successful predictions of the standard model is one of the most active areas of theoretical cosmology. At the most fundamental level, the level that most unsettles the field's deepest thinkers, the Hubble tension and the impossible early galaxies together might be telling us that the 2 pillars on which the standard model rests, dark matter and dark energy, are not what we think they are. Dark matter has never been directly detected. No particle that could be dark matter has been identified at the Large Hadron Collider, in underground detectors, or in the gamma-ray skies surveyed by the Fermi satellite. Its existence is inferred entirely from its gravitational effects on visible matter, and those gravitational effects might, in principle, be explained not by an unseen substance but by a modification of the law of gravity, a modification that looks like Newton's inverse square law on solar system scales but behaves differently on galactic and cosmological scales. Modified Newtonian dynamics, or MUND, is the most developed such proposal. It has struggled to explain the CMB without additional ingredients, but Webb's findings have given alternative gravity theories a new relevance in the field that has long been confident in dark matter's existence. Dark energy is even more poorly understood. The cosmological constant, the energy density of empty space that drives the accelerating expansion of the universe, has a value that is 120 orders of magnitude smaller than any calculation from quantum field theory predicts it should be. This cosmological constant problem is considered by many physicists to be the most severe fine-tuning problem in all of science. We know dark energy exists. The accelerating expansion has been measured beyond reasonable doubt. We have no idea what it is, and Webb's findings, particularly the Hubble tension, raise the possibility that dark energy may not be a constant at all, but may evolve over time in ways that change the expansion history of the universe. If Webb's observations eventually force a revision of our understanding of dark matter and dark energy, if the impossible early galaxies, the Hubble tension, and the early large-scale structure combine to point towards something genuinely new in the universe's composition, then the revision would be profound. We would be confronting a fundamental rewrite, not of the details of cosmology, but of the nature of 95% of everything that exists. The implications are not just academic. They cascade through every field of physics that touches cosmology, through the theory of gravity, through particle physics, through our understanding of the Big Bang and what preceded it, through our predictions for the long-term future of the universe. If the standard model is wrong, at a fundamental level, we do not just need a new cosmological model, we need a new physics. And the most extraordinary thing is that the instrument forcing us to confront this possibility is a machine that humanity built in the last 30 years, launched into space on a rocket and pointed at the edge of observable existence. The scientific community's response to Webb's anomalies has been creative, vigorous, and, in the best tradition of science, productively contentious. Several competing theoretical frameworks have been proposed, each attempting to reconcile the observations with some version of physical reality. Let us examine the most significant. The first and most conservative proposal involves modifications to galaxy formation physics. Standard simulations of galaxy formation, programs like Illustris TNG, EA-GALA, and the Santa Cruz Galaxy Formation Model, predict galaxy properties by modeling the physical processes of gas cooling, star formation, supernova feedback, and black hole accretion across cosmic time. These simulations have been tuned to reproduce the observed properties of galaxies in the nearby universe. but they are parametric. The underlying physical processes are simplified, and the parameters governing them are adjusted to match observations. If some of those parameters are wrong, if, for example, the efficiency of star formation in the early universe was significantly higher than current models assume, or if the feedback from the first generation of massive black holes was less efficient at suppressing star formation in early galaxies, then the galaxies Webb is finding might emerge naturally from modified versions of the existing framework. Several teams have explored this direction. Illustris TNG, modified to include a higher early star formation efficiency, can reproduce some of Webb's massive early galaxies, but not all of them. The most extreme objects, the galaxies with stellar masses 100 billion times the Sun's at redshifts above 10, remain beyond the reach of even aggressively modified simulations. The observation is outrunning the theory, and new physics may be required. The second proposal is early dark energy. In the standard lambda CDM model, the cosmological constant has always had the same value. Modifications that allow dark energy to have a higher value at early times, and to then decay to its current, lower value, change the expansion history of the universe in ways that affect both the Hubble constant measurement and the growth rate of structure. Several specific early dark energy models have been proposed and tested against CMB and large-scale structure data. Some of them can bring the Hubble tension into better agreement, but they do so at a cost. They tend to predict values of other cosmological parameters, particularly the amplitude of matter fluctuations, sigma and Caran, that are in tension with weak gravitational lensing observations. Every solution to the Hubble tension seems so far to create new tensions elsewhere. The third proposal involves modifications to the theory of gravity at cosmological scales. Einstein's general relativity has been tested with exquisite precision in the solar system, in binary pulsar systems, in the gravitational wave signals detected by LIGO and Virgo, and in the imaging of black holes by the Event Horizon Telescope. In all of these tests, it passes with flying colors. But general relativity has never been tested in the regime of the large-scale structure of the universe, where the density of matter is much lower and where the spatial scales are vastly larger than anything accessible to solar system or pulsar experiments. Modified gravity theories, most notably versions of MUND and its relativistic extensions, but also broader classes of scalar tensor theories and higher dimensional gravity models, make different predictions for structure formation and expansion history in this regime. Some of these predictions might be more consistent with what Webb is finding. The mainstream community remains skeptical of these alternatives, but the impossibility of direct testing in the cosmological regime means that the skepticism is provisional. The fourth class of proposal takes a step back from the specific anomalies and addresses the conceptual foundations of the standard model more broadly. Physicists, including Qumran Vafa at Harvard and collaborators, have been exploring whether the fundamental framework of string theory, the leading candidate for a theory of quantum gravity, places constraints on what kinds of cosmological models are physically consistent. Their swampland program, as it is called, argues that many versions of dark energy, including the cosmological constant as traditionally understood, may be inconsistent with a consistent theory of quantum gravity. If the cosmological constant is fundamentally incompatible with string theory, then the universe's dark energy must be something else, a dynamical field, perhaps, that evolves over time. And a dynamical dark energy might explain both the Hubble tension and aspects of the impossible early galaxy problem. None of these proposals has yet achieved scientific consensus. Each of them faces observational or theoretical challenges that its proponents have not fully resolved. The debate is live, the data continues to accumulate, and the resolution, when it comes, may involve elements from multiple proposals or something entirely new. The one thing is certain: the era of competent cosmology, or feeling that the standard model was basically complete and that the remaining work was filling in details, is over. Webb has ended it, and what replaces it will be forged in the confrontation between our best theories and the universe's stubbornly surprising reality. While the debate about impossible galaxies and Hubble tensions plays out in the journals and the conference halls, Webb has been quietly doing something else, something that, if confirmed, would be one of the most profound observational achievements in the history of astronomy. It has been searching for the first stars. In cosmology, the period between the release of the cosmic microwave background radiation, approximately 380,000 years after the Big Bang, and the emergence of the first stars and galaxies is known as the cosmic dark ages. During this period, the universe contained only hydrogen, helium, and trace amounts of lithium. No stars, no light, no nuclear burning, just a vast, dark, slowly expanding and slowly cooling gas. Primordial in the most literal sense, the raw material of everything that would come after, waiting for gravity to pull it into the first luminous structures. The first stars, designated Population 3 by astronomers, were unlike any stars that exist today. They formed from pristine gas with no heavy elements, without carbon and oxygen, which, in modern molecular clouds, act as coolants that allow gas to compress and fragment into smaller, denser clumps. The primordial gas clouds could not cool as efficiently. The fragments that formed the first stars were much more massive than modern stellar birth sites. Models predict that Population 3 stars had masses anywhere from tens to hundreds of times the mass of our Sun. They burned at temperatures that modern stars cannot sustain. They produced enormous fluxes of ultraviolet radiation, and they lived and died quickly, millions of years, not billions, ending their short lives in cataclysmic supernovae and, in some cases, direct collapses to black holes, seeding the surrounding gas with the first heavy elements the universe had ever known. Population 3 stars have never been directly observed. By the time they formed, in the first few 100 million years of cosmic history, and by the time they died, the universe was still too young to produce the galaxies we now observe. Their light, redshifted by the expansion of space into the infrared, is far below the detection threshold of any previous telescope. Only Webb, with its extraordinary infrared sensitivity, has a realistic chance of detecting their signature, not as individual stars, which remain below even Webb's detection limit at cosmological distances, but as a chemical fingerprint in the spectra of the first galaxies they inhabited and enriched. In 2023, a team including researchers from multiple institutions reported evidence of Population 3 stellar signatures in the spectrum of a lensed galaxy at a redshift, placing it at approximately 900 million years after the Big Bang. The spectrum showed unusual emission line ratios, particularly in the nitrogen and helium lines, that are inconsistent with the stellar populations of any known type of galaxy, but consistent with the presence of extremely massive, extremely hot stars of the kind Population 3 theory predicts. The finding was described as tentative, requiring confirmation, and subject to alternative interpretations involving exotic non-stellar sources. But if confirmed, it would be the first direct detection of the chemical legacy of the universe's first stellar generation. It would allow for the first time the testing of Population 3 star formation models against actual observational data rather than theoretical calculations alone, and it would close a gap in the observational history of the universe that has been open since cosmology began. Webb has also been mapping the process of cosmic reionization, the epoch between approximately 200 million and 1 billion years after the Big Bang, when the first stars and galaxies produced enough ultraviolet radiation to strip the electrons from the neutral hydrogen gas that filled the universe, transforming it from an opaque fog into the transparent medium it remains today. The timing and spatial pattern of reionization encode information about the properties of the first generations of stars and galaxies, how many there were, how massive, how bright, how concentrated. Webb's observations of the intergalactic medium during reionization, particularly its measurements of the Lyman alpha emission from early galaxies and the absorption patterns of quasar spectra at high redshifts, are providing, for the first time, a spatially resolved picture of how reionization progressed. The picture that is emerging suggests that reionization was patchy, proceeding faster in regions with high galaxy density and slower in the voids between them, and that the galaxies responsible for reionization were, on average, smaller and more numerous than the standard model's preferred scenario. This is again a result that is slightly at odds with predictions. Not dramatically so, not at the level of the impossible early galaxies or the Hubble tension, but consistently, in every deep observation it makes of the early universe, Webb is finding a cosmos that is slightly more surprising, slightly more structured, slightly more complex than the standard model allows. The cosmic dawn is not what we imagined, and every photon Webb collects from the edge of observable time is a piece of evidence in a case that is not yet closed. We have been approaching Webb's findings as scientific problems, as data anomalies, measurement discrepancies, theoretical crises that demand resolution, and they are all of those things. But they are also something more. They are reflections in the mirror of precision astronomy of something fundamental about the human project of understanding the cosmos. Consider, first, the nature of what Webb is actually doing. Every time it observes a galaxy at a redshift of 10 or 12 or 14, it is collecting light that left its source more than 13 billion years ago. The universe it is photographing is not the universe as it exists today. It is the universe as it was when the Earth did not exist, when our solar system had not yet condensed from the debris of an earlier stellar generation, when every atom in your body was somewhere else, dispersed in clouds of gas or locked inside a star or drifting through the intergalactic medium. Webb is a time machine, the most literal time machine humanity has ever built, and the past it is revealing does not match our models of what the past should look like. That fact, simple, data-grounded, verified by dozens of independent teams, carries philosophical weight far beyond the technical. For 50 years, cosmology has been building toward what physicists call the standard model of cosmology, a complete, coherent, mathematically precise account of the universe's origin, composition, structure, and evolution. The standard model has been one of the great intellectual achievements of the 20th and 21st centuries. It is quantitative. It makes predictions. It has been tested against independent observations and confirmed again and again to extraordinary precision. For a physicist in the year 2020, it felt approximately right, not certainly complete, but basically correct in its broad outlines, with only the details remaining to be filled in. Webb is suggesting that the broad outlines may be wrong. This is, in the history of physics, familiar and important. It is how science works. The Newtonian mechanics that predicted the behavior of the planets with extraordinary accuracy was deepened and extended by Einstein's general relativity, which predicted phenomena, gravitational waves, the bending of light by massive objects, the expansion of the universe that Newton could not have imagined. Relativity was not a rejection of Newton. It was a generalization, a more complete theory that reduced to Newton's equations in the appropriate limits while revealing the deeper structure beneath. The standard model of cosmology, if it is wrong in the ways Webb suggests, will likely be superseded in the same fashion by a more complete theory that preserves everything the standard model got right while explaining what it could not. The possible biosignature on K2-18b adds another dimension to the philosophical weight of these findings. If the dimethyl sulfide detection is real, if there is life in the ocean of a planet 120 light-years away, then the universe is not just more surprising than we thought. It is inhabited, and the question of what we are and where we fit in the cosmos takes on a completely different character. The search for life beyond Earth has always been one of the deepest expressions of human curiosity. The same curiosity that drives the search for dark matter, the measurement of the Hubble constant, the hunt for population 3 stars. It is the curiosity that says, the universe is vast, and we are small, and we want to know what else is here with us. If Webb finds even tentative evidence of that answer, if K2-18b's spectrum, when fully analyzed with more observations, continues to show a DMS-like signal, it will be one of the most important scientific findings in the history of our species. And it will raise immediately the question that every detection of possible extraterrestrial life raises. If life is there, 120 light-years away, found by the first telescope capable of detecting atmospheric biosignatures on a planet in a habitable zone, what does that mean for the prevalence of life in the galaxy? If we found it in the first handful of planets we looked at closely enough, in the first few years of operation of the first instrument capable of looking, what does that say about how many inhabited worlds there might be in a galaxy of 300 billion stars? The James Webb Space Telescope is not just an astronomical instrument. It is the most powerful investigative tool humanity has ever built for asking the questions that matter most. What is the universe? How did it begin? What does it contain? And are we alone? In the few years of its operation, it has already answered some of those questions, partially, tentatively, in ways that require further investigation, and it has opened new questions that will occupy science for decades. We built this machine to see the beginning of time, and the beginning of time does not look the way we thought it would. The universe is stranger than our models, more surprising than our simulations. More inhabited, perhaps, than our lowliness would suggest, we have covered the impossible early galaxies that challenge the standard model's account of the first billion years of cosmic history. We have examined the Hubble tension, the 5 sigma discrepancy that Webb has now confirmed and strengthened, pointing to something missing from our understanding of the universe's expansion. We have looked at the possible biosignature on K2-18b. We have explored the early large-scale structure that should not yet be organized, the tentative evidence for population 3 stars, and the patchy reionization of the early universe. But Webb is not done. It has been operating at full capacity for only a few years. Its nominal operational lifetime is 10 years, with sufficient fuel on board to operate for potentially 20. And the data it continues to gather, every week, every month, in dozens of ongoing programs targeting everything from nearby exoplanet atmospheres to the most distant galaxies humanity has ever observed, is producing new findings faster than the theoretical community can fully process them. In 2024, Webb's observations of galaxy clusters at intermediate redshifts began revealing details of the dark matter distribution, inferred from gravitational lensing, the bending of background light by foreground mass, that shows subtle but consistent deviations from lambda CDM predictions. The deviations are small, a few percent, and not yet at the level of statistical significance that demands a revision of the model, but they are in the same direction as every other Webb anomaly. The universe has more structure, concentrated more tightly at earlier times than the standard model predicts. The pattern across multiple independent observations is becoming harder to dismiss. Webb has also continued its survey of exoplanet atmospheres, building up the spectroscopic library that will eventually allow a rigorous statistical study of atmospheric composition across hundreds of worlds. The results are revealing a diversity of atmospheric types that exceeds what any model had anticipated. From the hot Jupiters with their exotic chemistries of iron vapor and titanium oxide, to the temperate sub-Neptunes with their atmospheric hazes and their tantalizing infrared features, to the rocky worlds whose atmospheres, if they have them at all, are barely detectable at the edge of Webb's capabilities. The picture of planetary atmospheres that is emerging is rich and complex and full of surprises, and the search for biosignatures continues. K2-18b is not the only target. Dozens of habitable zone worlds have been targeted by ongoing Webb programs, each accumulating transit spectra that are being analyzed for the chemical fingerprints of biological activity. The result? Confirmation or disconfirmation of the K2-18b DMS signal, and new measurements of other promising targets will emerge in the coming years. The answer to whether we are alone in the universe may already be encoded in data that is sitting on servers at the Space Telescope Science Institute, waiting for the right analysis. Here is what we know with certainty. The James Webb Space Telescope is working. Its instruments are performing better than their design specifications. Its calibrations are solid, and its data is high quality. The things it is finding are not artifacts of a flawed machine. They're real features of the real universe, measured with extraordinary precision by the most capable observatory humanity has ever deployed. And what it is finding does not match what we expected. The early universe has too many massive galaxies, too early, too structured. The universe is expanding at a rate that disagrees with itself. Two independent measurements, based on independent physics, giving answers that are 5 sigma apart and cannot both be right. A planet 120 light-years away may have chemistry in its atmosphere that, on Earth, is associated only with life. The cosmic web may have assembled earlier and more thoroughly than any simulation has been able to reproduce. None of these findings is fully explained. All of them are actively investigated. Each one, on its own, would be significant. Together, they paint a picture of a universe that is more complex, more surprising, and more resistant to our models than anyone who designed the James Webb Space Telescope anticipated. And yet, here is the thing that science teaches us. In every generation that has built better instruments and found that reality exceeded the models those instruments were meant to test. This is not failure. This is not the breakdown of science. This is science working exactly as it is supposed to work. The models we build are our best current guesses at the nature of reality. The instruments we build are the means by which we test those guesses. And when the tests come back with surprises, with anomalies, with things that should not exist and yet demonstrably do, that is the moment when science accelerates. That is the moment when the next generation of ideas is born. The impossible early galaxies will be explained, the Hubble tension will be resolved, the K2-18 biosignature will be confirmed or refuted, the early large-scale structure will be understood. New physics will be proposed, tested, confirmed or discarded, refined, and the picture of the universe that emerges from this process, the picture that Webb's findings have made necessary, will be richer, more accurate, and more extraordinary than the picture it replaces. This is the real story of what James Webb has found, not just the specific anomalies, as fascinating and terrifying as they are, but the larger truth that those anomalies represent, that the universe is under no obligation to fit our models, that reality is always more complex than our best theories, and that the appropriate response to that complexity is not despair but curiosity, the same curiosity that led us to build this machine in the first place, to fold its golden mirror into a rocket and send it to the edge of the Earth's gravitational reach and to point it at the beginning of time. We built the James Webb Space Telescope to see what could not be seen before. It has done that, and what it has seen is terrifying in the most profound and the most productive sense. Not the terror of the threat, but the terror of the unknown. The terror of standing at the edge of what you understand and looking out into the vast, dark, surprising, inhabited, possibly inhabited, certainly strange universe that extends beyond. The telescope is still watching. The data is still coming in, and the universe, vast and ancient and indifferent and full of secrets, has not yet finished telling us what it is. Look up. The universe is terrifying, and it is extraordinary, and it is ours to understand. There is something in the universe that you cannot see, cannot touch, cannot detect with any instrument on Earth, and yet without which nothing you have ever seen would exist. No galaxies, no stars, no planets, no you. It is called dark matter. It makes up approximately 27% of the total energy content of the universe, and it has never been directly detected. Not once, not a single particle, not a single collision in any underground detector, not a single signature at any particle accelerator, not a single photon from any indirect annihilation signal. Decades of searching, billions of dollars of experiments, and the only evidence for dark matter's existence remains what it has always been. The gravitational effects it produces on the visible matter around it, the rotation curves of galaxies, the bending of light by clusters, the pattern of structure in the cosmic web. Dark matter, inferred everywhere, detected nowhere. This would be uncomfortable on its own. But Webb has made it significantly worse, because Webb is measuring the distribution of dark matter in the early universe with unprecedented precision, using gravitational lensing, the bending of background light by foreground mass, and what it is finding does not match the predictions of the most successful dark matter models. The standard dark matter candidate is the WIMP, the weakly interacting massive particle, a hypothetical elementary particle predicted by supersymmetric extensions of the standard model of particle physics. WIMPs would have the right mass and interaction strength to have been produced in the right abundance in the early universe to match the observed dark matter density today. They would interact only through gravity and the weak nuclear force, making them invisible to telescopes but potentially detectable in underground laboratories where the occasional rare WIMP nucleus collision might produce a tiny pulse of light or heat. The Large Underground Xenon Experiment, the Xenon 1N Xenon experiments at Gran Sasso, the Panda-X experiment in China, and a dozen other underground detectors have collectively ruled out WIMPs over an enormous range of masses and interaction strengths. The parameter space in which WIMPs can still hide has been compressed to a small fraction of what theorists originally considered plausible. The WIMP is not dead. It remains theoretically possible. But it is, as physicists sometimes say, running out of room. Webb has added a new dimension to this crisis. Its observations of galaxy clusters at multiple redshifts, combined with gravitational lensing mass maps that trace the distribution of dark matter with extraordinary precision, have found that the central density of dark matter in galaxy clusters is lower than WIMP-based simulations of structure formation predict. In the centers of galaxies and clusters, WIMP should pile up, attracted by the deepest gravitational potential wells, accumulating in increasingly dense spikes called cusps. What is observed, both by Webb and by prior telescopes, is a flatter core rather than a sharp cusp. The dark matter in real galaxies is more spread out, more evenly distributed than the simulations predict. and Webb is now measuring this discrepancy at higher redshifts and higher precision than was ever previously possible. Two alternative dark matter models predict Discord behavior naturally: fuzzy dark matter, in which dark matter consists of extremely light bosons with wavelengths on the scale of galaxies, so that quantum mechanical wave effects smooth out the central density, produces naturally cooled profiles without requiring any baryonic feedback. Self-interacting dark matter, in which dark matter particles interact with each other through some dark force, not just through gravity, also produces cooled profiles, as the self-interactions thermalize the central regions and soften the cusp into a core. Webb's ongoing measurements of dark matter distribution in early galaxies and clusters will be crucial in distinguishing between these alternatives. But here is the deeper implication. If the WIMP model is definitively ruled out by the combination of underground detector null results and cosmological observations inconsistent with its predictions, then the leading particle physics candidate for dark matter, the candidate that has guided both detector design and cosmological simulation for 3 decades, is wrong, and the replacement must involve either new particles physics, new gravitational physics, or both. The invisible universe, it appears, is not quite what our models of it assumed, and what it actually is may be more strange and more interesting than the standard model ever imagined. While the cosmological debates about impossible galaxies and dark matter and the Hubble tension unfold in the pages of journals and the conference rooms of universities, Webb has been doing something quieter and in some ways more immediately transformative, building, for the first time in history, a systematic chemical library of the atmospheres of worlds beyond our solar system. Before Webb, the atmosphere of an exoplanet was, for most purposes, a box labeled "Contents Uncertain." Hubble's Wide Field Camera 3 and its Space Telescope imaging spectrograph had detected water vapor in the atmospheres of a handful of hot Jupiters, giant planets, in scorching close orbits around their stars, and a tentative few other molecules here and there. The data was sparse, the measurements noisy, the interpretations contested. The chemistry of other worlds was, in the most literal sense, mostly unknown. Webb changed this completely. In its first 2 years of science operations, Webb obtained detailed, high-quality spectra of more than 40 exoplanet atmospheres spanning the full diversity of known planetary types, from blazing hot Jupiters with their exotic chemistries of iron vapor and silicate clouds, to warm sub-Neptunes with hydrogen-rich atmospheres layered with organic molecules, to cooler worlds closer to Earth in size, where the nature of the atmosphere depends critically on whether the planet retains one at all. The hot Jupiter WSP-39b, observed during Webb's commissioning phase in the summer of 2022, provided the first demonstration of just what the telescope was capable of. Webb's NI spec detected in WSP-39b's atmosphere water vapor, carbon dioxide, carbon monoxide, sulfur dioxide, and sodium, the most comprehensive chemical inventory ever assembled for any exoplanet atmosphere. Carbon dioxide had been tentatively detected in one previous exoplanet atmosphere in a single noisy Hubble data point. Webb detected it in WSP-39b with overwhelming clarity, a clean, unmistakable absorption feature requiring no special statistical pleading, and the detection of sulfur dioxide was genuinely surprising. It is produced in WSP-39b's upper atmosphere by photochemistry, the same family of reactions shaping Earth's atmospheric chemistry, but the models had not predicted it would be detectable. Webb found it anyway, demonstrating that the chemistry of exoplanet atmospheres is richer and more complex than even the most detailed pre-Webb simulations anticipated. The temperate planets are where things get philosophically interesting. Webb has now observed several planets in or near the habitable zones of their host stars, and the results tell a story that is both encouraging and humbling. TRAPPIST-1b, the innermost of the 7 Earth-sized planets orbiting the red dwarf star TRAPPIST-1, was observed in 2023 through thermal emission spectroscopy. The measurements showed that TRAPPIST-1b is hot, approximately 230 degrees Celsius, consistent with a bare rock stripped of any significant atmosphere by the intense stellar wind and ultraviolet bombardment of its red dwarf host. TRAPPIST-1c, observed in the same campaign, told a more nuanced story. Its dayside temperature was lower than an airless rock would produce, but not low enough to indicate a thick atmosphere. The result is consistent with a thin atmosphere, or perhaps very high surface albedo, with further observations needed to distinguish the possibilities. The TRAPPIST-1 system is one of the most intensively studied in all of exoplanet science because its 7 Earth-sized planets, 3 of which orbit in the habitable zone, offer the best near-term opportunity to detect atmospheres and potentially biosignatures on terrestrial worlds. Webb will study the system for years, accumulating the statistical precision needed to detect thin atmospheres and probe their composition. Whether these worlds have survived their host star's turbulent youth with atmospheres intact is one of the most consequential open questions in exoplanet science. The chemical library Webb is building is not just a scientific resource. It is the foundation on which the search for life itself will be conducted. Every spectrum of every exoplanet atmosphere adds to our understanding of what chemistry looks like in the absence of life, giving us the reference frame against which the anomalous chemistry of a possibly inhabited world can be recognized. K218b's dimethyl sulfide signal is meaningful only because we are building that library. The library is being written, one spectrum at a time, by the golden mirror of the James Webb Space Telescope, and when the page that matters most is finally turned, we will know it because of everything written before it. The chemistry of other worlds is no longer a box labeled contents uncertain. It is becoming, one spectrum at a time, a library, and somewhere in that library there may be a page that changes everything. There is a light that fills the universe. It comes from every direction equally, at a temperature of just 2.725 degrees above absolute zero, and it has been traveling for 13.8 billion years. It is the cosmic microwave background, the CMB, the afterglow of the Big Bang, the oldest observable electromagnetic radiation in the universe, the fingerprint of the moment when the cosmos first became transparent and photons were set free to travel forever. The CMB is the bedrock of modern cosmology. Its temperature fluctuations, tiny variations at the level of 1 part in 100,000 across the sky, encode the initial conditions of the universe, the primordial seeds from which all subsequent structure grew. The Planck satellite, which mapped the CMB with extraordinary precision between 2009 and 2013, extracted from those fluctuations a set of cosmological parameters: the density of ordinary matter, and dark energy, the expansion rate, the geometry of space, that are the foundation of the lambda CDM model, and from those parameters, the Planck team predicted a Hubble constant of 67.4 kilometers per second per megaparsec. That number is the other side of the Hubble tension. The number that Webb has confirmed through its Cepheid measurements disagrees with that 5 sigma significance. But the CMB has more to say about what Webb is finding than just the Hubble tension. It also speaks directly to the anomaly of the impossible early galaxies. The initial conditions encoded in the CMB, the specific amplitude and scale dependence of the primordial density fluctuations, determine how rapidly structure can form in the early universe. If those initial conditions are exactly as Planck measured them, and the standard model of galaxy formation is correct, then the number and mass of galaxies at any given redshift is predicted with precision. Webb's impossible early galaxies violate those predictions, which means that either the initial conditions are different from what the CMB appears to show, or the process of galaxy formation is different from what the standard model assumes, or both. The CMB itself contains anomalies that remain unexplained. The hemispherical power asymmetry, a slight excess of temperature fluctuations on one side of the sky compared to the other, is present in the Planck data at a level of statistical significance that is difficult to dismiss as a fluke. The cold spot, an anomalously large and cold region in the southern celestial hemisphere, has attracted decades of theoretical attention, with proposals ranging from a supervoid along the line of sight to, more speculatively, the imprint of a collision between our universe and another bubble universe in the framework of eternal inflation. If either of these CMB anomalies is real physics, if they reflect actual features of the universe's initial conditions rather than statistical fluctuations, they point toward initial conditions that differ in subtle but important ways from the standard single-field inflationary model, and different initial conditions would change the predictions for early galaxy formation. More power on small scales, denser, more abundant fluctuations on the scales of the first galaxies, would produce more early massive galaxies more rapidly, potentially bringing the models into better agreement with Webb's observations. The CMB's anomalies and Webb's impossible galaxies may be speaking to the same underlying deviation from the standard inflationary model. Webb cannot observe the CMB directly. its wavelengths are too long. But Webb's observations of the early universe are, in this sense, a complementary probe of the same physics that the CMB encodes. Together, the CMB and Webb are measuring the universe from its earliest moment and from its earliest structures, cross-checking each other's implications and, in their disagreements, pointing toward new physics, the oldest light and the first galaxies. One measured at the beginning of everything, the other measured at the beginning of structure. And between them, a story that does not yet make complete sense. The CMB and Webb are speaking to each other across 13.8 billion years of cosmic history, and the conversation so far is revealing a universe that chose its initial conditions more strangely than any of our theories predicted. Buried at the center of almost every large galaxy in the observable universe is a supermassive black hole, an object of such extreme mass that its gravitational field warps spacetime completely, creating a region from which not even light can escape. Our own Milky Way harbors one, Sagittarius A, with a mass of approximately 4 million solar masses, photographed for the first time by the Event Horizon Telescope in 2022. The image, a glowing ring of superheated gas surrounding a dark silhouette, was one of the most arresting scientific images ever produced. A photograph of a singularity. A portrait of the void. The supermassive black holes in the centers of the most massive galaxies are far larger. The black hole at the center of the elliptical galaxy M87 has a mass of 6.5 billion solar masses. Others are larger still. The quasar TON 618, 10.4 billion light-years away, harbors a black hole of 66 billion solar masses, so massive that if it were placed at the center of our solar system, its event horizon would extend beyond the orbit of Pluto. How do supermassive black holes grow this large? The Standard Model has an answer built on two components. First, seed black holes, either stellar remnants of the first massive stars, or direct collapsed black holes formed when enormous gas clouds collapsed without first fragmenting into stars, provide the starting mass. Second, over billions of years, those seeds grow by accreting infalling gas, converting a fraction of that mass into the blinding radiation of a quasar and swallowing the rest, and merging with other black holes as their host galaxies merge. The process is well modeled, self-consistent, and in excellent agreement with the observed population of black holes in the nearby universe. The relationship between black hole mass and host galaxy mass. A tight correlation known as the M-sigma relation is one of the most precisely calibrated empirical relationships in astrophysics, until Webb. In April 2023, a team led by Rebecca Larson at the University of Texas Austin published a paper reporting the discovery of an extremely massive black hole, estimated at tens of millions of solar masses, in a galaxy existing just 570 million years after the Big Bang. At that age, even starting from the most massive theoretically allowed seed black holes and accreting matter at the maximum physically possible rate, the Eddington limit, at which radiation pressure balances gravitational inflow, a black hole cannot grow to tens of millions of solar masses. The required growth rate exceeds the Eddington limit by factors the Standard Model forbids. Multiple subsequent Webb observations have found what appear to be overmassive black holes whose mass is dramatically larger relative to the mass of their host galaxy, than the M-sigma relation predicts. A 2024 paper by Akos Bogdan and colleagues used X-ray data from the Chandra telescope in combination with Webb near-infrared imaging to confirm the existence of a massive accreting black hole at a redshift corresponding to just 470 million years after the Big Bang, potentially the most distant X-ray quasar ever detected. Its black hole mass was estimated at hundreds of millions of solar masses, far exceeding what standard seeding and accretion models can produce in the available time. Two explanations have attracted the most serious attention. The first is super Eddington accretion, a theoretical regime in which a black hole accretes matter faster than the standard Eddington limit by a large factor, radiating less efficiently and swallowing more of the infalling material rather than converting it to radiation. Super Eddington accretion has some theoretical support and has been proposed to explain certain unusual X-ray binary systems in the nearby universe, but whether it can operate continuously at the rates required to produce the early massive black holes Webb is finding is unclear. The second explanation involves more massive seed black holes than standard models assume, formed not by the collapse of individual massive population 3 stars, which would produce seeds of at most a few hundred solar masses, but by the direct collapse of gas clouds of much larger mass, producing seeds of 10,000 to 100,000 solar masses that would have a head start sufficient to reach the observed sizes by the time Webb sees them. What is clear is that the relationship between black holes and galaxies in the early universe is significantly different from what any current model predicts. Webb is revealing a black hole population that is, systematically and reproducibly, more massive, more luminous, and more advanced than the standard model's timeline allows. The monsters at the centers of galaxies are older than they should be, and what created them, and how they grew so fast, is one of the most urgent unsolved problems the telescope has uncovered. Something in the early universe was building the architecture of gravity at a pace that our physics cannot account for. And every new Webb observation of a distant quasar is a new brick in the case against the standard model. For the first few 100 million years after the Big Bang, the universe was dark. Not dark in the way a cloudy night is dark, or a windowless room, dark in the deepest possible sense. There were no stars, no galaxies, no sources of light of any kind. The primordial gas hydrogen and helium, the direct products of Big Bang nucleosynthesis, had cooled and spread through expanding space, neutral and opaque, absorbing any photon that attempted to travel through it. The universe was a fog. This period is called the Cosmic Dark Ages. It ended when gravity, working patiently in that darkness, compressed the first gas clouds to the density at which nuclear fusion ignited, and the first stars blazed into existence. Those first stars were powerful sources of ultraviolet radiation, radiation energetic enough to strip electrons from the neutral hydrogen surrounding them, ionizing the gas in expanding bubbles. As more stars formed, the ionized bubbles grew, merged, and eventually, by approximately 1 billion years after the Big Bang, filled the entire universe. The intergalactic medium transitioned from a neutral, opaque fog to the transparent ionized sea that allows light to travel freely across the cosmos today. This great transformation is called the Epoch of Reionization. The Epoch of Reionization is one of the last major phases of cosmic history that was, before Webb, almost entirely unobserved. The transition happened at redshifts between 6 and 15, a range that Webb, with its infrared sensitivity, is uniquely equipped to probe. And what it is finding is revealing a reionization process far more complex, far more spatially variable, and far more extended in time than any previous model predicted. Webb's primary tool for studying reionization is the spectra of distant quasars, the accreting supermassive black holes whose luminosity makes them visible across billions of light-years. When a quasar's light passes through neutral hydrogen gas in the intergalactic medium, the neutral hydrogen absorbs specific wavelengths in a characteristic pattern called the Lyman alpha forest. By studying this absorption pattern at multiple redshifts in multiple quasar spectra, Webb can map the neutral hydrogen fraction, how much of the intergalactic gas was still neutral, and how much had been ionized, as a function of cosmic time. It is, in effect, a time-lapse movie of the reionization process, played back through the spectra of the most luminous objects in the early universe. The movie Webb is assembling shows a reionization process that was profoundly patchy. Different regions of the universe were reionized at very different rates. Some areas were fully ionized by 700 million years after the Big Bang, while large voids remained significantly neutral for hundreds of millions of years longer. This spatial variation is far more pronounced than the standard model's inside-out reionization scenario predicts, in which ionized bubbles form first around the densest galaxy concentrations and expand outward into the surrounding voids. If reionization was this patchy, the galaxies responsible for it must have been extremely clustered, concentrated in specific overdense regions of the early universe, rather than distributed uniformly across space, and that clustering implies a large-scale structure in the early universe more developed than the standard model predicts, consistent with Webb's observations of proto-superclusters and early galaxy concentrations that should not yet exist. The reionization puzzle is, in this sense, another facet of the same underlying anomaly. The early universe was more organized, more structured, and more active than the standard model allows. Its galaxies were more massive, its black holes were more luminous, its large-scale structure was more developed, and its reionization was more spatially complex. Every probe Webb applies to the early universe returns the same result. Reality exceeds the model. The moment when the universe first became transparent, when the first light broke through the primordial fog, was messier, longer, and more spatially variable than anyone expected. And understanding it will require a new account of the first structures that made it happen. There is a feature of Einstein's general relativity that the James Webb Space Telescope exploits to see things that would otherwise be forever beyond its reach. It is called gravitational lensing, the bending of light by mass, and it transforms the universe's largest concentrations of matter into natural optical instruments of extraordinary power. When light from a very distant source passes near a massive object, a galaxy cluster, a concentration of dark matter, the gravitational field of that object bends the light's path, just as a glass lens bends visible light. The distant source is magnified, brightened, and sometimes split into multiple images, or stretched into arcs and rings. The effect was first predicted by Einstein, and first observed in 1919 during a solar eclipse, when Arthur Eddington's photograph showed that the positions of stars near the Sun shifted slightly from their true positions, exactly as general relativity predicted. A century later, Webb is using this effect on a cosmological scale, with galaxy clusters as the lenses and the farthest reaches of the observable universe as the objects being magnified. The results have been extraordinary. Webb's observation of the galaxy cluster, SMACS 0723, the image released as the first Webb science photograph on July 12, 2022, revealed dozens of lensed arc galaxies behind the cluster, several of which appear to be among the most distant galaxies ever imaged. The arcs, stretched and distorted by the gravitational field of the cluster, represent galaxies so faint and so far that without the cluster's magnification, they would be invisible even to Webb. The cluster is functioning as a cosmic telescope, amplifying the light of the ancient universe and focusing it on Webb's detectors. In 2023, Webb's deep observations of the cluster Abell 2744, one of the Hubble Frontier Fields clusters, already the subject of hundreds of previous papers, produced a lensed deep field containing thousands of background galaxies, many at redshifts placing them in the first billion years of cosmic history. The sheer density of early universe objects in a single Webb pointing of a massive cluster represents a qualitative leap in our ability to study the high redshift universe, a leap that the impossible early galaxy papers have been built upon. But gravitational lensing does more than magnify. It maps. The pattern of arcs and distortions in the light of background galaxies encodes information about the distribution of mass, including dark matter, in the lensing cluster. By carefully analyzing those distortions, using a technique called weak gravitational lensing, astronomers can reconstruct a map of the total mass distribution in the cluster, both visible and invisible. These dark matter maps, produced by Webb with higher resolution and greater depth than any previous telescope, are revealing a distribution of dark matter that does not perfectly match the predictions of WIMP-based simulations. One particularly striking result came from the analysis of multiple image systems in the cluster Abell 3827. In this cluster, a single background galaxy is split into 4 separate images by the cluster's gravitational field. The positions of these 4 images are extraordinarily sensitive to the precise dark matter distribution in the cluster. Small deviations from the predicted positions can reveal fine structure in the dark matter that simulations cannot reproduce. The observed offsets in Abell 327 are consistent with dark matter that is self-interacting, colliding with itself at rates far higher than WIMP models allow. If dark matter is self-interacting, it would require a dark force, some new interaction between dark matter particles that has no place in the standard model of particle physics. Webb is using the universe's own architecture as an instrument. The massive clusters it studies are not just targets, they are tools, concentrating and redirecting the light of the ancient universe to reveal what that universe contains. And what those natural instruments are revealing in the dark matter maps they produce is a substance more complex and more dynamic than the simple, collision-free, featureless WIMP model has ever assumed. The universe has been bending light with its gravity since the first structures formed. Webb is now reading those bends with enough precision to ask what exactly is doing the bending, and the answer is not straightforward. Everything we've discussed so far assumes a specific story for the origin of the universe, approximately 13.8 billion years ago. All of space, time, matter, and energy existed in a state of extraordinary density and temperature. It expanded. The Big Bang. The birth of the cosmos. Almost all cosmologists accept this story. The evidence for it is overwhelming: the expansion of the universe, the abundances of the light elements, the existence and properties of the cosmic microwave background, three independent pillars, confirmed to extraordinary precision. The Big Bang happened. But the Big Bang model, as originally formulated in the 1960s and 1970s, had a set of serious problems. Why was the universe so geometrically flat? Why was the CMB the same temperature in all directions, even in regions that, in the standard model, were far too separated to have ever been in causal contact? Why were there no magnetic monopoles predicted to have been produced copiously in the early universe by grand unified theories? These problems led, in 1980, to Alan Gough's proposal of cosmic inflation, a brief period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang, during which the universe grew from a region smaller than a proton to a volume larger than the observable universe today, in less than 10 to the power of minus 32 seconds. Inflation solves all three problems with elegant economy. It explains the flatness. Inflation stretched any initial curvature to near-perfect geometric flatness, just as inflating a balloon makes its surface appear flat on small scales. It explains the uniformity. Inflation took a tiny, causally connected region and expanded it to encompass our entire observable universe, so that the CMB looks the same in all directions because it originated from a region small enough to have reached thermal equilibrium. And it explains the absence of monopoles. The exponential expansion diluted them to a density too low to ever detect. Inflation is extraordinarily successful, but inflation has never been directly confirmed. Its most distinctive prediction, gravitational waves produced during the inflationary epoch, detectable as a specific B-mode polarization pattern in the CMB, has not been observed. The BICP2 announcement of 2014 raised hopes briefly before being retracted as a galactic dust artifact. The search continues with CMBS4 and the Simons Observatory. What Webb contributes to this debate is indirect but important. The details of inflation, the energy scale, the field dynamics, the number of fields involved, determine the spectrum of primordial density fluctuations that seeded all subsequent structure. Different inflationary models predict different amounts of power at different physical scales. If the initial power spectrum on the small scales relevant to the first galaxies was higher than the simplest inflationary models predict, if inflation produced more fluctuations on galaxy scales than standard slow-roll inflation expects, then the first galaxies would form faster and grow more massive, potentially matching what Webb observes. This is not a statement that inflation is wrong. It is a statement that inflation, if real, may have been more complex than the minimal single-field model that most theorists study. Multi-field inflation, resonance inflation, features in the inflaton potential that produce enhanced power at specific scales. All of these are observationally viable and would change the predictions for early galaxy formation in ways that might bring theory and observation into better agreement. As Webb's observations of the early universe become more statistically precise, as the number of high redshift galaxies it characterizes grows from hundreds to thousands, its data will become a progressively more powerful probe of the initial conditions, and through them, of the physics of inflation. The first structures in the universe are, in this sense, a record of the very first moment. A fossil of the Big Bang's most extreme early phase, written in the distribution of galaxies that Webb is now reading for the first time. The universe's first fraction of a second left its signature in the first galaxies. Webb is reading that signature, and what it says about what came before is still being decoded. The Hubble tension is the most famous of the cracks in the standard model, but it is not the only one. There is a second discrepancy, quieter in the popular press but equally significant in the technical literature, the sigma 8 tension, and Webb has deepened it. Sigma 8, written is a measure of the amplitude of matter fluctuations in the universe at a specific scale, 8 megaparsecs, a length corresponding to the typical size of a galaxy cluster. In plain terms, sigma 8 measures how lumpy the universe is, how much matter is concentrated in overdense regions compared to underdense voids. A high sigma 8 value means the universe has more pronounced structure, with more matter concentrated in clusters and filaments. A low value means the matter distribution is smoother and more uniform. Like the Hubble constant, sigma 8 can be measured in two independent ways. The Planck CMB measurement, using the standard lambda CDM model to project the observed early universe fluctuations forward to today, predicts a sigma 8 value of approximately 0.83. Direct measurements of the large-scale structure in the late universe, using galaxy surveys, cluster abundance counts, and most powerfully, weak gravitational lensing surveys, give values that are systematically lower, approximately 0.75 to 0.78. The universe, in late-time observations, appears less clumpy than the CMB-based prediction says it should be. The sigma 8 tension sits at roughly 3 to 4 sigma statistical significance, persistent across many independent measurements and many different methods. The Chi-DS survey, the DES survey, the Hyper-Suprime CAM survey, the Atacama Cosmology Telescope, all of them, using different telescopes, different galaxy samples, and different analysis methods, consistently find sigma 8 values below the Planck prediction. The tension is not going away, and it is not going to be explained by a single bad measurement from a single team. Webb has contributed to the sigma 8 picture through its gravitational lensing measurements at multiple redshifts. By measuring the distortion of background galaxy shapes by foreground matter at different cosmic epochs, near and far, Webb can trace how the amplitude of matter fluctuations has evolved over time. If the standard model is correct, sigma 8 should grow in a specific, well-predicted way as structure develops under gravity. If the growth is slower than predicted, if matter fluctuations at late times are genuinely smaller than the CMB implies, then something is suppressing the growth of structure across cosmic time. The preliminary results from Webb's lensing program suggest that the sigma 8 discrepancy is present at a range of redshifts rather than localized to a specific epoch. This is the signature of a long-acting mechanism. Perhaps a modification of dark energy's behavior over time, perhaps a property of dark matter that suppresses structure growth on small scales, perhaps a modification of gravity at large scales. The sigma 8 tension, taken together with the Hubble tension, paints a picture of a standard model pressed from two directions simultaneously. The expansion rate is too fast in the late universe. The structure is growing too slowly. Both discrepancies point to something wrong in the late-time behavior of the universe, in the behavior of dark energy, or dark matter, or gravity itself. That has been hidden until instruments like Webb and the latest lensing surveys revealed it. Two tensions in the same broad direction from completely independent observations. This is the pattern in the history of physics that immediately precedes discovery. The discovery, when it comes, will require something that is not yet in the standard model. And that something, whatever it is, will be the most important addition to cosmology in a generation. The universe is expanding faster than it should and clustering less than expected. Two symptoms. One disease, and the diagnosis has not yet been written. Stars die. It is one of the few certainties in an uncertain universe. Every star that has ever burned has burned through its nuclear fuel and reached an end, sometimes quietly, collapsing to a white dwarf and slowly cooling over billions of years into a cold dark cinder, sometimes catastrophically detonating in a supernova explosion that for a brief moment outshines an entire galaxy containing hundreds of billions of stars. The deaths of stars are not just spectacular, they are scientifically essential. Supernovae are the factories of the universe's heavy elements, the violent processes by which carbon, oxygen, silicon, iron, gold, and uranium are forged in the energy of a collapsing stellar core and scattered across the interstellar medium in an expanding shockwave. Without supernovae, there would be no rocky planets, no oceans, no biology of any kind. The calcium in your bones and the iron in your blood were made in stellar deaths billions of years before the sun existed. Supernovae are the reason you're possible, and one specific type of supernova, the type Ia, is the tool that earned Adam Rice, Saul Perlmutter, and Brian Schmidt the Nobel Prize in Physics in 2011. Type Ia supernovae occur when a white dwarf in a binary system accretes enough mass from its companion to exceed the Chandrasekhar limit, approximately 1.4 solar masses, and detonates in a thermonuclear explosion. Because the detonation always occurs at approximately the same mass, The peak brightness of a type Ia supernova is approximately the same, making it a standard candle that can be used to measure distances across billions of light years. It was through this method that Rice and Perlmutter and Schmidt discovered in 1998 that the expansion of the universe was not slowing down under gravity, but accelerating. The discovery of dark energy. Webb has transformed the study of supernovae in two specific and important ways. First, it has extended the type Ia supernova distance ladder to higher redshifts than were previously accessible. Hubble could detect type Ia supernovae out to redshifts of approximately 1.7. Webb, with its infrared sensitivity and superior resolution, can detect them out to redshifts of 2.5 and potentially beyond, reaching epochs when the universe was less than 3 billion years old. This extended sample covers a range of cosmic expansion history that was previously unmeasured, giving significantly more leverage on the properties of dark energy and whether its equation of state has changed over time. Second, Webb has been identifying and studying a population of supernovae in the very early universe that were never accessible before, the core collapse supernovae of the first massive stars. Core collapse supernovae occur when stars more massive than about 8 solar masses reach the end of their hydrogen-burning lives, can no longer generate the energy to support themselves against gravity, and collapse. The core imploding to a neutron star or black hole, while the envelope is expelled in an explosion visible across billions of light years. These events were the primary mechanism for distributing the heavy elements produced in massive stellar cores across the interstellar medium of the early universe. In Webb's deep field surveys, which monitor thousands of galaxies for brightness changes over time, transient events, objects that appear, brighten, and fade, are routinely detected. Some of these transients, at very high redshifts, have the light curves and spectral properties of core collapse supernovae from the first generations of massive stars. Some candidates, if confirmed, would be among the earliest stellar deaths ever observed, the first supernovae in the history of the universe, whose heavy element yields were the first enrichment of primordial gas with anything other than hydrogen and helium. The deaths of the first stars, observed 13 billion years after the fact by a telescope hovering in the cold of space, 1.5 million kilometers from Earth. It is, by any measure, one of the most extraordinary things that science has ever done. And the data those observations are producing, the yields, the explosion energies, the rates of the first supernovae, will constrain the properties of the population 3 stellar generation from the chemical output of their deaths. Stars died so that planets could form. Planets formed so that chemistry could organize. Chemistry organized so that biology could evolve. And biology evolved so that, eventually, one species could point a telescope at the deaths of the first stars, and read in those ancient explosions the history of everything that followed. The universe has a temperature. Not in the way a room has a temperature. Not uniformly, not everywhere the same, but in a deep, precise, cosmologically meaningful sense. The cosmic microwave background radiation fills all of space at a temperature of exactly 2.725 Kelvin, and this temperature is not static, it evolves. As the universe expands, the CMB cools, its photons stretch to longer and longer wavelengths by the expansion of space. In the distant past, the universe was smaller and hotter. In the far future, it will be larger and colder. This cooling of the CMB over cosmic time is one of the most fundamental and most precise predictions of Big Bang cosmology. The CMB temperature at any epoch in the past should be equal to 2.725 times 1 plus the redshift Kelvin. At redshift 1, when the universe was half its current size, the CMB should have been approximately 5.4 Kelvin. At redshift 3, when it was a quarter of its current size, approximately 10.9 Kelvin. The prediction is exact, unambiguous, and directly testable, and testing it requires measuring the temperature of the CMB not as it is today, but as it was billions of years ago. You cannot observe the past CMB directly. By the time those photons reach us, they have been redshifted to the present-day microwave wavelengths, and they're indistinguishable from the current CMB. But there is an indirect method, elegant in its ingenuity, that uses the physics of molecular excitation in distant gas clouds to measure the temperature of the CMB at the epoch when those clouds existed. Certain molecules, most commonly carbon monoxide, the second most abundant molecule in the universe after hydrogen, can only be excited to specific rotational energy levels by photons from the ambient radiation field. The ratio of molecules in different rotational states depends sensitively on the temperature of the radiation field surrounding them. By measuring this ratio through the absorption lines these molecules imprint in the spectra of background quasars, astronomers can infer the temperature of the CMB at the redshift of the absorbing cloud. It is a thermometer built from quantum mechanics, reading the temperature of the universe at epochs billions of years in the past. Webb has dramatically improved the precision of these measurements through its NIRS-SPEC spectrograph. Its ability to detect faint absorption features in the spectra of high redshift quasars with high signal-to-noise ratio allows molecular excitation measurements at redshifts, and therefore at CMB, temperatures that were previously inaccessible. The results so far are consistent with the expected temperature-redshift relationship. The universe does cool as it expands at the rate the standard Big Bang model predicts. This is a confirmation of the model that stands alongside its anomalies. But here is where cosmological subtlety enters. If the properties of dark energy change over time, if the equation of state of dark energy deviates from the cosmological constant value of -1, then the expansion history of the universe, and hence the cooling rate of the CMB, would be slightly different from the standard prediction. As Webb's CMB temperature measurements at high redshift become more precise, they will contribute to the constraints on dark energy's equation of state, complementary to the supernova distance ladder and the baryon acoustic oscillations measured by DESI. The temperature of the universe, measured in the spectral signatures of cold gas clouds billions of light years away, is a cosmological thermometer probing the properties of the dark energy that determines the expansion history and, ultimately, the fate of the cosmos. Every measurement Webb adds to this record is another data point in the reconstruction of the universe's thermal history, and another constraint on the nature of the invisible energy that is, slowly, inevitably, pulling everything apart. The universe is cooling. It has been cooling since the moment it began, and every degree of that cooling carries information about what drove the expansion. Information Webb is, molecule by molecule, spectrum by spectrum, patiently reading from the cold gas between the galaxies. For all the attention devoted to Webb's deep universe findings, the impossible early galaxies, the early supermassive black holes, the population theory candidates, it is easy to overlook what the telescope is revealing much closer to home, because Webb is not just a machine for looking at the edge of the observable universe. It is the most powerful infrared observatory ever deployed, and its capabilities transform our understanding of objects across the full range of cosmic distances, from the planets of our own solar system to the star-forming regions of the Milky Way, to the galaxies of the nearby universe. Within our own solar system, Webb has produced results of extraordinary scientific value. Its observations of the outer solar system have revealed atmospheric chemistry and cloud structures with a precision that no previous telescope could achieve at infrared wavelengths. Jupiter's auroras, imaged by Webb in July 2022, showed structures and variability at a level of detail that is changing our understanding of how the gas giant's magnetic field interacts with the charged particles flowing in from its volcanic moon, Io. Webb captured in a single infrared image features of Jupiter's atmosphere, jet streams, anticlones, the Great Red Spot, together with its rings and two of its moons, at a level of detail that left planetary scientists reaching for superlatives. Neptune's rings, the finest and most tenuous ring system in the outer solar system, barely visible even in the best Hubble images, appeared in Webb's first infrared observations with a clarity not seen since Voyager 2's flyby in 1989. Ring structures that Hubble showed only faintly resolved into distinct components in Webb's images, revealing the complex photochemistry of Neptune's upper atmosphere alongside the delicate geometry of the rings themselves. The observation was, in the words of the Webb team, the clearest view of Neptune's rings in more than 3 decades. And then there is Titan, Saturn's largest moon, the only moon in the solar system with a thick atmosphere and liquids on its surface, is a world of such unique complexity that it has been called a laboratory for prebiotic chemistry, a place where organic molecules rain from the sky and accumulate in lakes and seas on the surface. Webb has observed Titan at infrared wavelengths that pierce the photochemical haze obscuring its surface to visible light telescopes, revealing cloud systems in its northern hemisphere. Surface brightness contrasts between the dark organic lakes and the brighter icy highlands, an atmospheric chemistry that will directly inform the Dragonfly mission. NASA's nuclear-powered rotorcraft lander, scheduled to arrive at Titan in the early 2030s. Beyond the solar system but within the Milky Way, Webb has been revolutionizing the study of star formation. Its infrared sensitivity allows it to pierce the dense molecular clouds within which new stars are born, clouds opaque to visible light but transparent to infrared, revealing the protostars within, them at stages of formation inaccessible to any previous instrument. The image of the Carina Nebula, released in July 2022, showed the dramatic landscape of a massive star-forming region, the Cosmic Cliffs, as the team named them, with a clarity and depth that no previous telescope had achieved. Webb revealed previously invisible protostars emerging from their dusty cocoons, jets of superheated material erupting from newly forming stellar objects at hundreds of kilometers per second, and the intricate structure of gas and dust pillars sculpted by the relentless radiation pressure of massive young stars. These observations are not just beautiful, they are scientifically transformative. The properties of the protostars Webb is revealing, their masses, temperatures, accretion rates, and jet properties, are the inputs to our understanding of how stars of different types form and how the process of star formation affects the surrounding interstellar medium. The Carina Nebula images alone have produced dozens of papers probing the physics of stellar birth with a precision that will inform stellar models for decades. The universe of nearby things, the planets, the nebulae, the star-forming clouds, has been transformed by Webb just as surely as the distant universe has. Everywhere it looks, the telescope finds that reality is richer, more detailed, and more complex than our models predicted. Everything in the universe is being pulled apart, not by any mechanical force, not by an explosion into pre-existing space, not by any material substance pushing outward. The expansion of the universe is the expansion of space itself, the fabric of space-time stretching, driven by the energy density of the quantum vacuum. Dark energy, the repulsive force that fills every cubic centimeter of the universe, growing stronger as the universe expands, inexorably accelerating the separation of everything from everything else. Dark energy was discovered in 1998, when two independent teams, Saul Perlmutter's supernova cosmology project and Brian Schmidt and Adam Rice's High-Z supernova search team, found that distant Type Ia supernovae were fainter than expected. Fainter means more distant. More distant means the universe had expanded more than a decelerating cosmos would allow. The universe was not slowing under gravity. It was accelerating. Something was pushing it apart. That something received the name dark energy, and its discovery rewrote cosmology. Dark energy makes up approximately 68% of the total energy content of the universe. Its simplest description, as a cosmological constant, an energy density that is the same everywhere and does not change over time, fits all current observational data. But it comes with the most severe fine-tuning problem in all of physics. When physicists calculate the energy density of the quantum vacuum from first principles using quantum field theory, they get a number approximately 10 much square times larger than the observed cosmological constant. This 120 order of magnitude discrepancy, the worst prediction in the history of physics, has no accepted theoretical explanation. In 2024, the Dark Energy Spectroscopic Instrument, DESI, reported tantalizing hints that dark energy might not be a true cosmological constant. DSI analyzed the baryon acoustic oscillation signal, the characteristic spacing between galaxy concentrations imprinted by sound waves in the early universe, in more than 6 million galaxies at multiple redshifts. This analysis measures the expansion history of the universe at different cosmic epochs, and the best-fit dark energy equation of state turned out to be inconsistent with the true cosmological constant at approximately 2.5 to 3 sigma significance. Dark energy might be evolving, growing stronger or weaker over cosmic time, rather than remaining fixed at its constant value. The implications of evolving dark energy are profound. A cosmological constant drives the universe toward the heat death, an infinitely cold, infinitely thin, infinitely expanding void in which all structure has long since dissipated and the last black holes have evaporated. If dark energy is phantom energy, stronger than a cosmological constant, with an equation of state more negative than -1, the universe ends instead in a big rip. The accelerating expansion eventually overcomes all forces, tearing apart first galaxy clusters, then galaxies, then solar systems, then planets, then molecules, then atoms. A finite time singularity in which the universe is dismembered from the largest scale to the smallest. If dark energy is weakening and will eventually reverse, becoming attractive rather than repulsive, a big crunch is possible, the expansion slowing, stopping, reversing, the universe collapsing back to a singularity. Webb is contributing to the dark energy investigation through its extended Type 1 supernova survey and its deep gravitational lensing measurements. Its supernovae at redshifts above 2 probe the expansion history at epochs earlier than DESI's primary sensitivity, extending the baseline over which the dark energy equation of state can be constrained. Its lensing measurements probe the growth of structure, differently sensitive to dark energy than the expansion history alone, providing an independent constraint that breaks degeneracies in the cosmological parameter fits, in the data Webb is collecting, in the light curves of ancient stellar explosions, in the lensing maps of galaxy clusters, in the absorption spectra of the most distant quasars, is encoded the answer to one of the deepest questions in all of science. What is the nature of the energy that makes up 2/3 of the universe? And what will it do to the cosmos in the end? The fate of everything, of every galaxy, every star, every planet, every atom, depends on the true nature of dark energy. And Webb is measuring it, one supernova at a time, one lensing map at a time, moving toward an answer that, when it comes, will be one of the most consequential facts in the history of science. We have now traveled through 26 chapters of what the James Webb Space Telescope has found. From impossible early galaxies to the Hubble tension, from a possible biosignature on K2-18b to overmassive black holes, from dark matter anomalies to the reionization puzzle, from the deaths of the first stars to the evolving nature of dark energy. It is time for an honest accounting. What has Webb actually established? What remains uncertain? And what comes next? What Webb has established, beyond reasonable scientific doubt, is this: the standard model of cosmology, lambda CDM, is incomplete. This conclusion follows from multiple independent lines of evidence analyzed by multiple independent teams using multiple independent methods. The Hubble tension alone, a 5 sigma discrepancy between the early universe and late universe measurements of the universe's expansion rate, now confirmed by Webb's Cepheid observations with greater precision than any previous instrument, would be sufficient to conclude that something is missing. The impossible early galaxies, the overmassive early black holes, the dark matter core cusp problem, the sigma-8 tension, the patchy reionization, and the DESI hints of evolving dark energy all reinforce this conclusion from entirely different directions. The standard model is not wrong in the sense of having been falsified. It remains the most successful quantitative model of the universe ever constructed, but it is incomplete. Something is missing, and that something is causing it to fail at the frontier where Webb is operating. What Webb has not established is which of the many proposed modifications to the standard model is correct. Early dark energy? Self-interacting dark matter? Fuzzy dark matter? Modified gravity? A different inflationary history? An evolving equation of state for dark energy? All of these are in play. None of them has yet been confirmed. The data from Webb is extraordinary, the anomalies are real, the need for new physics is clear. But the specific form of that new physics remains unknown. This is where science is, past the stage of denial that there is a problem, actively working toward the stage of identifying the solution, but not yet there. The instruments that will help find the solution are being built. The Via Rubin Observatory, now entering science operations in Chile, will survey the southern sky for 10 years with unprecedented depth and cadence, mapping the large-scale structure of the universe across cosmic time, measuring the properties of dark energy and dark matter through weak gravitational lensing, cluster abundances, and galaxy power spectra, with a statistical power that will dwarf any previous survey. The Euclid satellite, launched by the European Space Agency in 2023, is mapping the large-scale structure of the universe in near-infrared and visible light across billions of cubic megaparsecs, the most powerful dark energy survey ever conducted from space. The CMB-S4 experiment and the Simons Observatory will push CMB measurements to new levels of precision, potentially detecting the gravitational wave signal of inflation and independently measuring cosmological parameters with sub-percent precision. And Webb itself continues. Every week, Its queue of approved science programs produces new data, new spectra, new images, new gravitational lensing maps, new transient detections, new atmospheric measurements. The telescope has operated for a few years of a planned mission of at least 10, with fuel reserves sufficient for potentially 20. Every year adds to the extraordinary body of evidence it is assembling. The anomalies it has found will grow stronger and more precisely defined, or they will be explained by modifications to the models that turn out to be sufficient after all. Either outcome advances science. The K2-18b biosignature question will be resolved, or deepened, by more Webb observations and by the eventual launch of future space telescopes designed for atmospheric characterization of nearby terrestrial planets. The Habitable Worlds Observatory, recommended by the 2021 Astronomy and Astrophysics Decadal Survey and endorsed by NASA, is designed specifically to image Earth-like planets around nearby Sun-like stars, to look directly at the nearest potentially inhabited worlds and read their atmospheric chemistry. If life exists on any planet within roughly 40 light-years of Earth, the Habitable Worlds Observatory will have the capability to detect its atmospheric signature. The search for life beyond Earth is moving from a project of listening, of hoping that a radio signal will emerge from the static, to a project of looking, of systematically examining the atmospheres of nearby worlds and asking what their chemistry reveals about what lives beneath their skies. Webb did not find a single terrifying thing. It found many things that are, each in their own way, terrifying. It found that the early universe produced massive galaxies faster than physics allows. It found that the universe is expanding faster than its own early history predicts. It found chemistry in the atmosphere of a distant planet that is produced, on Earth, only by life. It found black holes that are older than black holes should be. It found dark matter distributions that do not match the behavior of the leading dark matter candidate. It found the epoch of reionization to be messier and more complex than any model had predicted. And it found, in the first hints from Daisy, that dark energy may not be constant, a potential crack in the most fundamental component of the cosmological model. These are not failures. They are the specific, hard-won, irreplaceable discoveries that only precision instruments operating at the frontier of knowledge can produce. They are the moments when nature speaks clearly and tells us, "You are not yet right. Your model is not yet sufficient. Look again, look harder. Look with better instruments and more open minds." The James Webb Space Telescope is one of humanity's most extraordinary achievements, not because it confirmed what we knew, but because it showed us what we didn't. Not because it resolved our questions, but because it made those questions inescapable. Not because it found the answer, but because it showed us with unprecedented clarity exactly where the answer is hiding. The mirror is still turning, the photons are still arriving, the universe is still speaking, and we at last have built an ear fine enough to hear it. The story has not ended.